So the recording, it's about the armor formula. So I'm going to review a bit about the canopy formula, but this time as if I were in an exam facing a question that asks, explain the first order linear differential equation with variable coefficients and derive the canopy formula for its solution. So here it is. A first order linear differential equation with variable coefficients is an equation that can be written in this form. Y prime plus a function f of x times y is it? It is with another function, g of x. If a differential line can be written to look like this, so it is first order. Why? Because what I'm looking for is y, and it is differentiated once. That's in the name first order. It is a differential equation with variable coefficients, because those and those are two functions that are known. They are variables, they depend on x, those are the coefficients. And it is linear. Why? Because its solution has the same solution structure as the solution to a linear system of lines. And how was the solution for a linear line system? It was a particular solution for the line plus the complete solution to the homogeneous form of the line. I'm not sure if you remember it, but otherwise I can just repeat it. And you can solve this differential equation using the formula that looks like this. Y equals Euler's number raised to the power of the negative antiderivative of f times a large parenthesis where it says the integral of g of x multiplied by Euler's number raised to the positive antiderivative f of x. And dx is used to close the integral sign there.
And then
it is some constant g and that constant k. And I would like to prove that. And to prove that this is the solution to that problem, I start by writing down this differential equation and then using the clever idea 1r and multiplying the equation by Euler's number raised to capital F. If I do this right away, it says y prime times e raised to the capital F plus lowercase f of x times y times e raised to the capital F. So now I have multiplied the first term and the second term by e raised to the power of capital F. Then I also need to multiply the right side by e raised to the power of capital F. And now we see why it was a good idea. Because everything written here can be rewritten as I am about to write. So this, and I would like to explain it, if I need to differentiate with respect to x a product of two functions, namely that function and that function, then I have to use the product rule. And the product rule says that I differentiate the first factor times the second factor unchanged, plus the first factor unchanged times the second factor differentiated. So I need to differentiate e raised to the power f. What does that give? Well, it gives e to the power of capital F itself, but you have to remember that it's a composite function. So you need to multiply by the derivative of capital F, which gives small f, and that's shown there. Then I need to multiply by y unchanged, as it is shown there. So this entire term is what you get first when you differentiate this product. That is the first factor differentiated times the second factor unaltered, which is shown here. Then I need to do the reverse in between.
With an advantage.
So I write plus. First factor untouched, that is EF, it is written here. Multiply by the second factor differentiated, that is shown there. It's marked. So now I've convinced myself that this is the same as that. And on the right side, it still shows Gax times Euler's number raised to the power of x. What I want to find is y, so I would like to eliminate this differentiation process, and therefore I integrate both sides with respect to x. And when I integrate something that is already differentiated, it just gives the core, which was capital E raised to capital F times y. And then an integral sign appears on the right side because I also need to integrate with respect to x. And since it is with respect to x, this is what I need to write. And here I write bx, which means I have integrated with respect to x. And then we know that we need all solutions. So we say plus k to get all solutions. In
Zip file doesn't require adding plus k.
One can wait to write plus k until the day you calculate the integral. But then you have to remember it, and most people forget. That's why it's smart to write plus k now. Strictly speaking, it's something you actually need to do later. What I want to find is y. So I isolate it by dividing by this factor on both sides, e raised to the power of capital F. But dividing by it is the same as multiplying by e to the power of negative capital F. So you could say I'm multiplying the equation by e to the power of minus capital F. It's like I'm undoing what I started with, because what did I start with? It was multiplying by e to the power of capital F, and later multiplying by e to the power of minus capital F.
But what has been achieved is that y has been isolated.
So this needs to be multiplied by this, but there are two terms, so I should put parentheses to make sure it's applied to both terms. And there are indeed some mathematicians who don't write plus k here, and then you don't need parentheses if you don't write plus k. But if you belong to that group of mathematicians, you just need to remember that the day you use the formula, when you calculate this integral, you must write plus k. Because when we calculate an indefinite integral, you must always write plus k. So that is the integrating factor formula. And now I would like to show what I can use the integrating factor formula for.
So here comes an example.
I would like to show that you can use the AMA formula to solve this differential equation, which is y prime plus a times y equals b. Because over here, it is a first order linear differential equation with two variable coefficients. This is a first order linear differential equation with two constant coefficients. So let's see if we can use this formula to solve it. And the only thing you need to do to solve it is to note that the a there corresponds to the f here, f prime of x, and the b there corresponds to g prime of x. So if this is f prime of x, and that is g prime of x, I can simply assign f prime of x to be a, and g prime of x to be b, and use the same formula.
So I have to stand here.
So let's do that.
The solution becomes
To what
completely
the solution to that differential equation will be
Euler-style uplifted in
Minus
mine.
an antiderivative for.
if
And what is an antiderivative
There
for
is
the
a
constant
constant.
a? Well, it's just the constant times x. Because a is
it
extra.
is confronted, it yields.
It
And
is
now I
along
click.
the square bracket you see here. And then there comes an integral sign.
And g of x becomes b. So here I write b.
And then multiply e raised to a primitive function of a, well, that's x. And then dx, and then plus k.
So we can continue calculating it. This integral can actually be solved quite easily.
I just copy pasted this down. Then I think that a constant that is multiplied should be placed in front of the integral.
e in the x is integrated, that's obvious.
But it is a composite function. So I have to remember to divide by times x differentiated. Because that would have been multiplied if I were differentiating. But I am integrating. So I should not multiply by a, I should divide. So I claim that this is an antiderivative of that integrand. Is that correct? Well, let's just try to differentiate this. The b is a constant, so it stays there. E to the x differentiated gives itself. If you remember to multiply by a, then a cancels out
It's
with it.
a, and then exactly b, a in x, as it should be.
And finally, I need to write plus k. Some people only write plus k now, after they have calculated it. But there is the risk of forgetting to write plus k. And that's why I have decided to stick to writing plus k, also in the formula. Then I can take that function and multiply it into that term, and that function and multiply it into that term, and then I'm done. Then I have the formula. And if I multiply that by that, you can see it says e to the negative x times e to the positive ax. Well, that gives e to the 0, because you can add the exponents together. So with 1 times the fraction, that's a part. It just gives b prime apart, because 1 times b prime apart is b prime apart. And when I multiply it into that, it says plus k.
Gang e is minus.
Minus a times x, where k is some real number. And this
Is it a complete solution?
for the differential equation that has this form. And now I will show you what I talked about with why it is called
But
that.
the differentiation just about.
Maybe you remember that when you had a linear system of equations,
That's what the solution looked like.
What's this? The solution looks like this.
x vector solution was equal to some particular solution. plus the complete solution. For the homogeneous case,
This is what the solution looks like for
always.
DNet.
And if you write it in standard parametric form, I'm not sure if you remember it. So like out here, some kind of weight here. Plus t times some vector here. This is the solution structure if there is one free variable, 3 equations with 3 unknowns. And that is a particular solution. So if y is
X.
2 and z is 3, it should solve the linear system. And over here, this is the complete solution if it were the corresponding homogeneous linear system, where there is simply 0 on the right side. Perhaps I should show you a specific example from linear algebra so you can remember it. But now look, this is what's written here. Can you see there are 2 things added together? Here, this is a particular solution to the differential equation. That's the first thing I want to show you. And this here is the complete solution to the homogeneous version of the same differential equation. So where it simply says 0.
It is with dividers.
So you should just take a look at the structure. In other words, what we call the structure theorem. It also applies to differential equations. And this is new compared to what you had in high school. You don't hear about this principle in high school. But you can see that my solution, y, is called b over a.
Lucen constant.
And I claim that this is a particular solution to the differential equation. What does that mean? It simply means that if I set y to be b over a, it should solve the differential equation.
Does it? What does the Y mark mean?
If y is just called the ending part.
Well, it is a constant.
Constant and a constant
Let's say it
constant.
equals 0.
So here it will show 0. Can you see it when I put it in?
So YP label gives 0.
So 0 plus, and then I have to say 0 plus a times y. But I was this key pass. And then I test if it gives b in front of each value of x. Does it? Well, it does, because a goes away. And it's true that b equals b in front of every value of x. So what does that mean? It means that this is a solution to the differential equation, but it is a very particular specific solution. That's why I call it y sub p. The next thing I concluded is that this is the complete solution.
Solution for the homotopy.
Imagine now that there is a 0 over there. Then it is called the homogeneous case. Then I would get a differential equation that says y prime plus a times y equals 0. And it fits that this satisfies it. So let's try to find y prime, if that is y. K to the power of minus ax. What does that give when you differentiate it? It gives itself. K to the power of minus ax. But you must remember to multiply by the inner function, which gives minus a.
Because differentiating minus x gives minus a. Are you following that?
And then it says
Plus a
and then
times
like
plus
a times a, but what was e again? Oh yes, it was that. That was what I claimed I was. So k times e to the power of minus ax. And now see what that gives. They are the same with opposite signs. So it equals 0. And the differential equation stated that it should equal 0 if it is homogeneous. What does it prove then? It is the complete solution to the corresponding homogeneous line. And it holds for linear differential equations that their solution structure is such that the complete solution is equal to a particular solution of the differential equation itself, plus the complete solution to the corresponding homogeneous version of the same differential equation. And what I've asked you to practice isn't everything I've just talked about, but only the first part. So now we pause the recording and we practice presenting it to each other. Let's pause the recording here. All right, so the first order linear differential equation with variable coefficients, it looked like this. Y prime plus some function.
You know, corridor y.
should include some function that one is familiar with.
If it looks like this, or can be rewritten to look like this by simply dividing or multiplying by something clever. For example, if there were a function here in front, then you can just divide through by it, so it takes this form. Then you can solve it using this formula, known as the Armour formula.
and that is the one we just derived together.
And if we multiply out, just like Mads did when he was at the board, we get this term times that plus this term times that.
And we'll do that so it says e to the power of lowercase f once integrated by g.
E and I plus store f. That is x, and then plus key times that factor out there. And what we need to show now is that there
And that one is yours.
two terms that play a role in the solution structure.
So what I would like to show is that this is the complete solution.
For the homogeneous case. So I have written FLH for the complete solution to the homogeneous case. That's where it says 0 over here. And this is a particular solution to the differential itself. I would like to convince you that it is correct. So to do that, I will consider this differential equation again, but with 0 on the other side. So the homogeneous version is equation star. And it looks like this.
The homogeneous version of stars.
It is called y prime plus f of x times y equals 0. That one, you can solve that quite easily. And when you solve it, you get that. Let's try that. So I will just write down the differential equation. And instead of writing y prime, I will write di over dx, because that is another way to express y prime. So I just replace y prime with another notation for the same thing, di over dx, and then plus f of x times y equals 0. And this derivation I'm doing now is also very clever to get a handle on for the oral exam, because it's really good to demonstrate. So to find y, I think, okay, y is both there and there. Can I do something clever to gather the y's on one side and the x's on the other side? And this method is called separation of variables.
So I am now using that method to create separation
Of the variables.
So what will it say now?
To
And then I
begin
just
with,
write
is
it
y.
is x equals negative f of x.
So what I've done now is simply taken that term and subtracted it from both sides of the equation sign. Now I do something clever. I divide by y over here and multiply by dx over there.
For if I do that, then
Something
everything
related to y
and
altogether.
everything related to x is gathered on the right side.
And if there was a mathematician in the mix, he would ask why you're simply dividing by y. And then I would say yes, unless y is 0, of course, then I can't divide by it.
So let's consider the special case where y is 0.
So consider this with me. What happens if y is equal to 0?
If y is 0, what does di dx give?
0, because y equals 0. That's the function whose graph lies right on top of the x-axis. So the graph is just right here, directly on the x-axis. That's y equals 0. What slope does it have?
What does di dx become then? Is it true at 0?
is equal to something times 0. Yes, that's true. No matter what this something
Unless
is.
it is infinite.
Imagine that the fax behaves nicely, it does not act up. Then we discover that u is a solution
To the differential line. So y equals 0.
Yes, a solution.
And this is called the trivial 0 solution. And they say it's boring because it doesn't really convey anything physical, other than the fact that the function, which is always 0, also solves the differential equation. That's usually not the one you're interested in finding. We want to find all the solutions that are not the 0 solution. So now that we have considered y equals 0, we can simply assume that y is not 0. And now we have thought about it.
So if y is not 0, then I am allowed to divide by
It will then have an equation with y.
Then there will be a graceful part.
Multiply by dy. Nevertheless, minus f of x times dx. I hope you followed what I did there. So up here, I divide by y, bringing it down to the denominator. But dividing by y is the same as multiplying by 1 over y. And the dx that was here, I move it over to the other side. which is why it says times dx there.
Is that okay?
Now I want to integrate on both sides because I want to find y. So I integrate on both sides, hoping to find y. So I integrate here. And that integral sign means I integrate with respect to y. And then I integrate over here. But that integral sign means I integrate with respect to x.
All right, and what do I know about y? It is certainly not 0, as I've assumed. If it were 0, the universe would explode here, where I divide by y's.
So now it says, can't you find all the antiderivatives for a function of y with respect to y? Yes, I can. It's just the natural logarithm of the numerical value of y. Because what does the natural logarithm of something differentiated give? 1 over something. Okay, and why have I written some more absolute value signs? It's because I don't know if y is greater than 0 or less than 0. And you can only take the natural logarithm of something positive. That's why I've added more absolute value signs. And over on the right side, I need to integrate lowercase f, but that just gives uppercase f. And then we must remember that when we perform such an indefinite integral, a constant appears.
Keep going. Can I join in on that?
And that constant, I could call it k, which I initially used here, but I think I'll actually call it little c now, because I plan to do some small tricks with this constant. Well, I am a bit closer to finding y now. Can you see it? The only thing I need to do to isolate y is to remove len. And what is the inverse of taking the natural logarithm? It is exponentiating with Euler's number as the base. So the opposite is taking the natural logarithm. It is raising to an exponent with Euler's number as the base. So I use Euler's number like this and say e raised to the power of lny numerically equals e raised to the power of minus big F of x plus c. I hope you can follow that. Now you can see that these two operations cancel each other out because they are inverse functions. They are each other's inverse mathematical functions, so they disappear. So I am left with just the numerical value of y. Nevertheless, but this can be written a bit more cleverly. You can write it like this: e to the power of c times e to the power of negative capital F by using an exponentiation rule. There is a rule that says e to something plus something else is e to the one times e to the other. It is one of our exponent rules. And if c is a constant, what does this become? Also a constant. I now call it capital K.
So I christened the big K. It is a constant. But not only is it a constant, I know it can only be positive.
E in something can only produce something positive. So this capital K belongs to the set of positive real numbers. So what do we have now? We have that the numerical value of y is equal to a constant capital K times e to the negative capital F of x, where I know about k that it can only be positive real numbers. So we're almost there. I just need to remove the numerical sign. How do you do that? Well, if the numerical value of something unknown gives blah, 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 what does the unknown give? Plus or minus blah, blah, blah. Where do you think about it? The numerical value of something you don't know should be 3.
What should x be then? Either 3 or negative 3.
So that means if the numerical value is
Right,
y,
then y itself is either plus or minus that. Are you following? And then we're basically there because that plus or minus can just be absorbed into a constant, which we call small k. Now it says that y equals small k times e to the power of negative capital F. And if big K could only be positive, what can small k be? Both positive and negative. And if we also allow it to be 0, which solution do we also get? 0 solution. So why not just tell ourselves that we have it figured out now? Little k can be any real number.
And here's the complete solution.
To what? To the homogeneous version of the stellar equation.
Because that was the one I started with. And you can see it's standing here.
And echo e in a negative capital F.
K is a minus stor F.
Are you following that? So what I have shown you now
when
is
Hans
that the
receives
formula
two contributions,
contains to the complete solution y. And one contribution is the complete solution to the corresponding homogeneous differential equation. And what I still need to convince you of is that that is a particular solution to the differential equation. And what do I mean by that? That should ideally solve the differential equation. It definitely should.
And it all is a solution too.
But the complete solution is not here, it is over here. You need to include both things. That is just one specific solution, while here, they are all together. Can you see the difference? And that's the thing with linear equations. What is always their solution structure? A particular solution to the equation plus the complete solution to the corresponding homogeneous equation. If an equation behaves like this, we call it linear. And there is something nice and linear about it. Are you with me on this? So on the next page, we will just convince ourselves that this here...
YP actually solves the star equation. So what did our star equation look like again?
Oh, right, it's just called y prime plus f of x times y equals g of x. Let's try substituting yp into it and see if it works.
So we insert YP
and do a test.
So to insert, I apparently need to differentiate y.
Put it in there. So I need to leave it alone. Insert it there. Then I need to remember to multiply by f on y. And then I check if it gives g. If it does, then it was a solution.
So let's start by finding the YP brand. And where was it that YP was standing? It was right here.
So now I need to find this differential percentage. And since it's a product, I differentiate the first factor times the untouched second factor plus the untouched first factor times the differentiated second factor. Here in front, when I differentiate e to the power of negative capital F, it is straightforward.
But I need to remember to multiply by the differentiated
and that gives minus lowercase f because it is a composite function. And capital F differentiated gives small f. But capital F with a minus sign differentiated gives small f with a minus sign.
And then I will multiply by the other one untouched.
Then it is just the integral of dx times e in large F.
Then I'll do
It's
it
the other way around.
plus, and I'm on it.
What differentiates? Plus, I need to leave the first factor untouched, which means e to the power of negative capital F. And that happens times the differentiated integral. But integration and differentiation are inverses of each other. So it just gives the inner part. The integral sign disappears.
So that just gives times g of x. Gang A. We always join in on that.
all that. Should I try to insert there now?
Because it is the y mark I have found. And then I have to say plus f times y unchanged. And then we'll see if it gives g. So let's try it.
So I copy and paste all of that.
We insert. In that star equation up here, then we get e to the power of negative uppercase f.
Times negative little f of x. Multiply the integral of g.
E store fx. Bx. Plus e and minus store f. Crank in x. Gangi is in ILF. Now there is something left
Then
here.
I
I have to say plus f of x times y.
So plus f of x.
What was ye? Oh, right, it was all of this. So I'll just paste that up. Is it a bit of a bother? I won't try to do this for the exam. E minus f.
Times the integral of g.
Scene one in the story. And now let's see what all this results in. And let's take a look. Can you see that there?
Okay, there it is.
And that one, isn't it the same with the opposite sign?
Or is it? I might just need to go back a bit so you can see it.
That is not quite it. No.
isn't it? That one. Isn't it quite similar to this one? Because here there is a minus, but here there was a plus. So they are completely opposite, and they cancel each other out. But then only this is left. And what does e to the power of minus f times e to the power of plus f give? It gives e to the power of 0, which is 1, times g. Oops, then it gives g. And it gives g for any value of x. So that was a solution. So the conclusion is that yp is one particular solution. Now you have seen that the solution structure is the one we are familiar with from linear algebra. You don't need to do that for the exam. It was just to show you what the structure is like. If you can derive the Panzer-Drengen and answer the rest of the questions, which I will now put out. I had forgotten. And now I've said it on video, so I've committed myself to it. That's fine, then now I'll go down and write out some differential equations for you to practice and post your oral questions. And then have a great weekend. I'm going to the Blow Bloom concert later, and I am really looking forward to it. See you.